Our session today will start with Xiaodong Zhu from University of Washington. Welcome.
Yeah. I'd like to thank the organizer for the invitation. And today I'm going to show you this fraction quantum anomalous effect. So as requested by our organizer that this will be a tutorial. So my plan is that give you a background of this effect. Then I will discuss this experimental evidence to support this FQH effect. Then at the end of my talk, I'll give you some kind of latest results from my group. Okay. So the effect I talked to you is belong to these quantum Hall families. And we all know that, right? In the setup of a 2D electron gas and in the application of a strong magnetic field in the vertical directions. So in the measurement of these Hall conductance, actually were quantized and is described by this formula here. And with C, now we know its chain number, and the unit of E squared of H. So C can be an integer, then it will be integer quantum Hall effect. Or C can be a fraction value, then it will be a fraction quantum Hall effect. And all these effects they discovered at the early 1980s. So there's something remarkable about this discovery, where as you see that this Hall conductance is quantized precisely in some fundamental constants. And this will become even more remarkable if we look at the first sample, right? The first gallium arsenide sample used to measure or discover the fraction quantum Hall effect. Right? The sample itself is of a few millimeters. And you can see that all these electrode contacts, all these wires, right? Nothing compared to the state-of-the-art of these devices we had today from electron beam lithographies. And if you look at the surface samples, there's a lot of dust. I assume they're silver paste, actually. Now you look at such a kind of, I would say it's kind of lousy samples, but they give you beautiful quantizations. So they tell you something amazing happened in the physical systems, right? It tells you why, govern why these collective phenomena of electrons actually give you these precise quantized values. So now we know that this amazing property is called topologies, right? So pointed out by my colleague David Solis, right, in a couple of papers with his collaborators, right, shows that the origin of these quantum Hall effect is coming from these topologies. So the essence is described by this formula, now we know as TKKN formula. But this formula actually is useful for both integer and the fraction quantum Hall effect. So the key idea is that the integral of a barrier curvature of the first Baryon zone of momentum space and give rise to these chain numbers. And precisely it's the quantized Hall conductors. So for the original derivation of these quantized Hall effect, actually the paper itself actually doesn't involve the lambda levels, and it's in particular for the second paper when they derive these fractional values, they don't even involve magnetic field. Magnetic field is not necessary. So when I talked to actually Chen Niu, actually 6 months ago, so he told me that the time, even though they didn't involve magnetic field to calculate these many body chain numbers, but they didn't really appreciate this important, because the time when they do these calculation, all they care about is they want to figure out where's the origin of a topology for the fraction quantum Hall effect. Right? That was 1984. Yeah. So, but I want to just emphasize that the derivation itself actually doesn't involve magnetic field. There's a lot of amazing physics, right, associated with this fraction quantum Hall effect. And one example is it's a manifestation of anions. So anion itself is strange quasi-particles, right, in a two-dimensional world. Here I give you a very kind of a simple way to show what an anion is, right? In a 2D system, imagine we have two indistinguishable particles at the positions R1 and R2. Then the wave function can be written down as psi and R1 and R2. Now what we're going to do is we're going to exchange the positions of these two particles. Then we end up with final wave functions, right, with psi, then R2 and R1. So from the quantum mechanics, we know that these initial wave function and the final wave function can be connected by this formula with the phase in the front, e to the I theta. And the theta can be 0, which describes bosons, and theta can be pi, which describes fermions. That's what we know. But in the 2D, actually, theta can also be a rational fractions of pi. And these give rise to these anions, right? The name actually given by Frank Wilczek in these papers. So initially, anion was an abstract concept until the discovery of this fraction quantum Hall effect. Then Bert Hoplin and also Frank Wilczek and his collaborators and realized that these fraction quantum Hall excitations actually follow these fractional statistics, and actually it's an anion. Then there's a lot of development after this. For example, right, when the even denominator fraction quantum Hall still was discovered, such as 5/2, then there's another kind of theory development to describe the system can be host non-abelian anions. So anion is not only of fundamental interest, and pointed out by Kataev, right? Anion actually can be used as a candidate for topological qubit, then realize these fault-tolerant quantum computations. So here I steal the diagram right from this review paper. So the key idea is that right for the anions, they have this reduced Hilbert space. What it means is that the wave function is only determined by the positions of these particles. So if you want to change the wave functions, then you have to swap the particles. Now we know as exchange as a braiding operations, right? So what that means is that if you have local perturbation on these each particles, it doesn't really change wave functions. Then these will protect from the quantum decoherence. So there's a lot of proposals and use these anions for non-abelian anions for topological quantum computations. Right? 5/2 is one of the prime candidates for that. And there's a lot of proposals, right? One example is you can interface superconductors and with fraction quantum Hall edge states. Then you can create a certain type of non-abelian anions, in this case called parafermions. And there's a lot of efforts in these directions, right? How you can realize this effect. Here, a highlight example from Philip, Amir, right? The collaborations. So they basically create this graphene device and interface with niobium nitride superconductors. So they were looking for these non-abelian excitations, but it turns out to be challenging because you at least requires 10 Teslas to create these fraction edge states. And then these 10 Tesla will create these vortex in the superconductors, actually kill these non-abelian anions. So you can see that the challenge of all these proposals using this fraction quantum Hall effect is that first, right, fraction quantum Hall effect itself is very fragile and requires high magnetic field. So these kind of pose challenges for these routine operations. The second is that we all know that superconductors, right, doesn't like high magnetic field. So these pose another challenge. Then what we need is we'd like to have these fraction quantum Hall effect, hopefully at the high temperatures, and doesn't require magnetic field. So that's the fraction quantum anomalous Hall effect. So the concept for the quantum Hall without these lambda level formation, right, has a long history. And here I highlight work from Duncan, right? He basically proposed these concrete models, how you can realize these quantum Hall without magnetic field in these toy models. So you can see in his paper, right? He said, the political model represented here is unlikely to be directly physically realizable, but at the end he concluded, right? It's possible to realize the effect in occur as a consequence of a magnetic ordering in a quasi two-dimensional systems. So Duncan's model doesn't consider spin auto coupling, so it's a spinless model. At the early 2000s, Eugene Milley and Charlie Kim proposed this model, which is included spin orbital coupling in the system. Then they realized these Z2 quantum spin Hall effect with Z2 topological orders. So the key idea, once you have these spin orbital coupling, right, you can consider this Kim-Lee model as two copies of Hall-Dam model. Right? One is with spin up, the other with spin down. They are degenerate. So you can get a quantum spin Hall effect, as you heard yesterday from Phi. But if you apply magnetic field, then you can break the symmetry between these up and down copies, right? Then you can create a single copy of a Hall-Dam models. So that's probably one way to realize this quantum Hall effect, but without the magnetic field, or we call quantum anomalous Hall effect. So the quantum anomalous Hall effect was first realized by the group led by Qikun Xie in China. So they used these magnetically doped two-dimensional topological insulators. And here I showed the main experimental evidence, right? If you look at these Hall resistance, right? These different curve represent different gate voltage, means tune the Fermi level. So when they tune the Fermi level inside a gap, you will see that this rho xy is quantized in a unit of Hc square at the zero magnetic field. And the same on the right-hand side, right? The blue curve is rho xy, the red is rho xx. So basically, when the Fermi level inside gap, you will see rho xy is quantized, and with rho x is strongly suppressed. But everything happened at the zero magnetic field. So that's the key, right? Or the hallmark of a quantum anomalous Hall effect. And now the question is whether it's possible to realize this fractional version of this QH effect. And there's actually a lot of theory progress in these directions. For example, right, back to the late 1990s, right, Bob Laughlin considered this fractional quantum Hall effect, right, in a spin lattice systems. There's also Nick Reid has these considered this fractional quantum Hall effect in periodical potentials. Then there's the early 2000s, right? There's a development of this code-adding system for quantum simulations. Then there's a lot of progress in how to realize this fractional quantum Hall effect in the optical lattice. But all these proposals still requires magnetic field to break down result symmetries. Then the concrete idea of this zero magnetic field fractional quantum Hall effect was established at the 2011. There's several theory papers, and the material at the time when realized this effect called the fractional chain insulators. So the key ingredients to realize this FQH effect is that you need the band need to be topological, and we need the strong electron interactions, right? And then lastly is we need a spontaneous time reversal symmetry breakings. So this provides effective magnetic field, even though we don't apply the external magnetic field. And if you want to summarize, right, we need a flat chain band to do this. So then how to find a useful flat chain band? And thanks to Alan, right, he talked yesterday too, that Alan, right, his collaborator realized that in a match angle twisted Hall bilayer graphings, you can create these flat bands. And as you heard from Alan yesterday, right, this idea is pretty general for the 2D systems. There's probably a lot of materials. When you twist them, some angles, it will give you a flat band. And the group led by Pablo at the MIT, we all know, right, 2018, they has these remarkable discoveries of unconventional superconductivities, right, in these match angle graphing. So really tells the power of these systems. So motivated by these all these breakthroughs, now the researchers in the field start to think about, can we create these flat chain band and realize this FQH effect? So here I highlight the field theory work about the realization of a CX in twisted graphings. Then in the same directions, right, the integer quantized anomalous Hall effect or QH effect actually being realized both in graphings and also in twisted TMDs. So the challenge is still there, right? How we can realize these fractional versions. So there's attempt in the graphing communities. So the work led by Andrea Yang, right, from Santa Barbara, they have these Mori superlattice formed by bilayer graphing on hexagonal boron nitrides. And when the magnetic field is above 30 Tesla, so they have these states behave like fractional chain insulator states. And the work also in collaboration between Pablo and Amir Yacobi, right? They use match angle twisted bilayer graphing. So in this case, they can lower the magnetic field to 5 Teslas, and as they see states, right, behave like fractional chain insulators. Again, as I mentioned too, right? There's still a challenge, right, to realize this effect at the zero magnetic field. So that's what I'm going to talk to you today. Right, last year, my group actually found that we can realize these fractional quantum anomalous effect, or FQH, in twisted MOT2 bilayers. So initially, we have evidence of a 2/3, 3/5, and 4/7 states, and then later on this year we have, in collaboration with other groups, there's 2 new states appeared. So I highlight the 3 works. Right, the first one is we found the spontaneous ferromagnetism in such a system, which shows that the first criteria, right, we need a time reversal symmetry breakings. And the second is we use the optical technique to map out the Venn diagram. Then we use the strata formula analysis to show there's a signature of these FCI states. And lastly, we perform the transport measurements to show there's actually fractional quantized states. And as you heard from Fai yesterday, right, the effect itself is very robust. Now has been observed by many groups. And here I highlight all the works appeared, either published or appear online. And you also heard from Longji yesterday, right, in addition to the twist MOT2. Now we have another system, which is a multi-layer graphene for these FQH effect, has been seen now in several groups. So today's talk, right, I will just go over these 3 works. Then I will show you some new results from my group. So let me give you a brief introduction of these materials. Right, it belong to the family of transition metal dicogenite. So here I show you the crystal structure from monolayer TMDs. They have these hexagonal lattice structure, and the corners of each these hexagonal lattice. The one is cocktail atom, the other metal atom, so the inversion symmetry breaks. So once this inversion symmetry is broken, my collaborator Di Xiao and Wang Yao, they realized that there's a valley dependent battery curvature and also orbital magnetic moment. One of the key features I'm going to talk to you later is that we have these valley-dependent optical selection rules. So for one valley, you couple signal minus Paris light, and the other you couple the signal plus. So when you stack these materials, right, with a homo bilayer and with a slightly twist, then we can form these honeycomb-like structure in these Mori sublattice. So within a single Mori unit cells, there's a 2 energy degenerate point, called B and C. So B is with metal on top of cocktail, and the C is with cocktail on top of metals. Okay, they are energy degenerate. Then they form these honeycomb lattice. And our work is really motivated by these breakthrough from Allen's group. Right, they show that right, the Mori bands of a twisted homo bilayers, right, can become topologically non-trivial, and in particular, in twisted bilayer MOT2. So that's what this Allen's paper is, give us the directions to go. And the Allen paper shows that right, when you have these layer pseudo spin skyrmions, right, as you heard yesterday, then the system can have these hosted K-Melee models. If the strong interaction itself can break time reversal symmetries, then, as I told you at the beginning, right, then this K-Melee model can become Houdin models, and there's a possibility to realize these anomalous Hall effect. Here I show you the scan tunneling microscopy study done early this year from my colleague, Matt Youngowitz. So the middle panel shows the topographic image of this twisted MOT2 bilayer at a 2.7 degree twisted. So you can see that really we have these honeycomb lattice, right? He mapped out these MX, XM domains. Then he also imaged the denser states from the K-valley flat bands. So he really shows that the dense states is localized at these MX or XM points. So that forms these honeycomb lattice, as I just mentioned to you. It's confirmed by this STM study. So the contribution from my own group is that first, right, we found this spontaneous ferromagnetism. So bottom right is the device structure. We have this dual gated structure with twisted MOT2, and then we can control doping and also electric field across the samples. Here I also define the filling number, mu, which is the number of carriers per Mori unit cells. So what we do here is we use these magnetic circuit dichroism measurements. You can think of it as optical absorption difference between left and right circular Paris light. It's a measurement of Hall conductivities at the optical frequencies. Now the data I show you these MCD measurements at the zero magnetic field. Right? The color, red color means there's finite signals. So the vertical axis is the filling number. Again, right, when I see filling -1, means there's a 1 hole per mole unit cells. And the horizontal axis is the electric field. So you can see that in the phase space of Hall dopings, near filling factor -1, right, there's non-vanishing MCD signals. This signifies these ferromagnetic phases in this phase space. And in particular, right, you can already see that there's hump features at the fraction filling -2/3. So if we zoom in of these MCD signals, and we can plot the MCD at the selected filling factor as function magnetic field. So you can see we do see hysteresis, right, in a range of filling factors. So let's highlight that we do have a ferromagnetism in existence, and the magnetism itself actually has a strong filling independent. For example, if I just plot the hysteretic component of the signal as function filling number, you will see that the cohesive field actually dramatically enhanced at the fraction filling -2/3, and particularly at the integer filling -1. So that's already give you a hint, right? There's something going on in the systems. So to probe this topological nature of the states, yeah, please.
How do you determine the filling factor experimentally?
Yeah, so we have many different type of correlated states in the systems. So we basically assign the filling factor based on the states together. So that gives you a pretty strong confidence what's the filling numbers. Of course, there's errors, but yeah.
Okay, I see.
Yeah. Then the technique we use is trion sensing. So let me just briefly mention, right? In semiconductor, when you shine light, you can create excitons, which is bounded by electron holes. It's a neutral exciton. Now imagine we start to dope the system with holes, right? In dilute dopings, means the screening effect is weak. Then these excitons can bond to actual holes from a charged excitons, which is a trion. So spectroscopically, we can tell the difference between exciton trions. Here I show you the luminescence spectra from a monolayer MOT2, right? The top curve is from a charged neutral exciton luminescence. The bottom is from a trion luminescence. You can see that the energy is different, right? Distinguished by about 20 milli-electron-volt, and also the intensity is different. So use that, we can probe the correlated states in the systems. So here I show you the PL intensity plot of a twisted Wiley MOT2. And the vertical axis, again, is a filling number. Horizontal is the energies. Now you can see that there are three features here, right? I marked the filling factor -3/5, -2/3, and -1. So the trion signal actually is quenched at these three filling factors. And a simple way to understand it, right? A trion is, it's a neutral exciton bound to extra carrier, right? So if there's an incompatible state formed in a system, then the Fermi surface got to gap out. So the number of free carriers is reduced, then the number of trion will be reduced. A direct consequence of this suppression of a trion population, right, is the suppression of luminescence intensities. So now we can use a trion as a probe, observable of these incompressible states. Then what we do is we just measure these trion luminescence as function of a magnetic field in these vertical axis. And the horizontal is just the doping and the filling factor label on the top. Now you can see that the red is features, filling factor 1, 2/3, and a faint one at the -3/5. So we can extract the density correspond to these depositions and the plot in the bottom. They actually agree really well with the strata formulas. So this gives us the signatures of these quantum anomalous Hall state and also these fractional changeless state, the 2/3 filling and also -3/5 fillings. And we can also measure, right, in many different samples. Here, sort of a little bit improved signals. You can, right, without this just raw data, we haven't done any massage. You can already see that the fraction fillings, right, at 2/3, 3/5, and that's another one at 4/7. Yeah, here just the align with these strata formulas. So far I show you how we can, right, give the signatures of these fractional changeless states. use these Schroeder formula analysis. Now I'm going to switch gear, talk about the transport measurements of this effect. Here I show you the device of a 3.7 degrees taken at the 100 millikelvins. So on the left-hand side with longitudinal resistance measurements of RxX, and right-hand side is Hall resistance measurements of RxY. Now let's look at RxX first, right? There's a lot of features in the plot, but the blue color, right, represents the vanishing RxX. Red means a very strong resistance, and we see black means just too large to measure. So what we have here is near filling factor 1, we have a large phase space, right? This RxX is vanishing, and correspondingly in RxY, with large signal, actually it's quantized at HV squared. So that's the corner anomalous Hall phase. And then there's another state at minus 2/3 fillings with a pocket of suppressed RxX and with enhanced RxY. So that's the fraction Chancellory state. Then we can also have another state with near minus 1/2, which is suppressed RxX, but with very large RxY. And this is a putative composite film liquid state. So we can look into details of these states. For example, right here, I show you the quantum anomalous Hall state at the filling factor -1. So what I show you the bottom panel is this RxY measurement as function magnetic field. The top is our corresponding RxX. So the effect itself is highly reproducible and is independent of has a very has a little dependence on the twist angle. So far we can see this quantized anomalous Hall effect from twist angle 2.6 degree all the way to 4.2 degree in my own lab. And also, I think the Cornell group also shows there's a quantized Hall effect at the 2.1 degrees. And the other feature I would point out is that the effect has a high temperature, means there's a large gap associated with distance. Here I show you the temperature dependence, right, from these minus 2/3 of FCI states. From top is 100 millikelvin all the way to 3 kelvins. So you can see the effect, the Hall signal still nearly quantized at 2 kelvins. So on this panel, I show you the extracted RxY signal as function temperature. So you can see that right, over almost 2 order of magnitude of temperature change, right, from 2 Kelvin all the way to tens of millikelvins. This RxY is all the way quantized. Okay, so these are slightly different from these rhombohedral graphene Long talked to yesterday. We don't see these phase transitions from quantum anomalous Hall, for example, FCA, to these extended quantum anomalous Hall effect. So we haven't seen it in the twisted TMD system. So so far I talked to you, all the results we have, and then I'm going to show you some new results. So the initial challenge of the field, both for graphene and for TMD, is that for most devices, right, is even though we see quantized RxY, but the RxX actually has a large value, few kiloohm. So this is kind of a puzzle. We don't know where it's coming from, but we always say, okay, probably due to disorders, right? That's when you don't know what's going on, just always blame disorders. So we're looking into the materials, see if we can improve the crystals. So here is what we've done with conductive AFM. We image these crystals, counting the defects from companies, right, commercial crystals. So use conductive AFM, we can image certain type of defects. We don't know the origin of these defects, right? We don't know who they are, but at least we can count them. So you can see that there's many bright dots represent a certain type of defects. Right? We can count them, and the defect density is on the order 10 to 11 per centimeter squares. There could be other defects in the system we don't see. Then I have a drawing postdoc, Chaowei Hu. He's really talented, right, with my colleague Junhao Chu. So what I told Chaowei is, okay, well, could you grow some clean crystals? That's all I told him. Then he went back to lab and spent a long time trying to figure out the way to grow these crystals. He tried many different ways. And eventually, he able to grow clean crystals. So here's the same kind of a conductive AFM imaging of the crystal grown by Chaowei. Now you can see that with this image, right, over 50 times 50 nanometer, for example, we only have one defect. Okay, now the defect density is lower to 10 to the 9th per centimeter squared. So this crystal, right, we grown in our lab right now has defect density two order magnitude lower than the commercial ones. So I'm going to show you the results from these type of new crystals. On the left-hand side is the measurement of RxX, right? I just talked to you a few slides ago from these commercial crystals. And the right-hand side is this same longitudinal resistance measurement from a new device from our own crystals. You can see these two qualitatively, right? They're similar, right? You see there's a quantum anomalous at the filling factor -1. You even see these EF features, the same EF features, okay? And you can see electric field induced phase transitions, right, from quantum anomalous to insulating state, likely to a Mach state. You see the same thing here. So everything looks the same. You can also see the -2/3 state with a little pocket, and you can see -2/3 states. And the difference is that the new crystal looks cleaner. Then we can see another pocket in this feature with a -3/5 state, which doesn't show up here. And what I highlight is that when I tune the electric field, right, for this -2/3 state, we have phase transition from this fractional translator to a charge order state, right, with a strong resistive peak. By the -3/5 states, we don't see the formation of charge order in a large electric field. Now I can take line cuts of RxX, right, which is the red curve, and RxY is the blue curve as function of a filling factor. Now you can see that these RxX, right, at the 2/3 fillings almost approach 0, and with also a strong dip at the -3/5 fillings, and with another small dip at the -4 fillings, and some other wiggles at the even lower filling factors. So you can zoom in on these, just zoom in on the fractional filling side, right? These, again, I just want to highlight. Now, these RxX really approach zeros at the -2/3 fillings. And the -3/5 filling is only out of 2 to 3 kiloohms. And I suspect it can be even lower if we can improve the contact of the systems. Okay, so now I want to bring attention to another feature I just mentioned to you, which is this putative composite film liquid state. So here's the data from the first device I showed you, right? Here I show you these RxY, the blue curve, as function filling factor. So interesting feature is that when these filling factor, right, small, near half fillings, you see these RxY will increase linearly as the filling number and across two edge of these squares. But we don't see any plateau feature here, okay? At the half filling, right? All we see is a linear cross and at the two edge of these squares. So if we measure this signal as function of magnetic field, you will see there's a strong hysteresis. So this only means that the signal itself indeed is anomalous Hall signals. Doesn't mean it's quantized, okay? So what's going on, right? And we can compare it to the optical measurements, and we see that there's no suppressions of this PO intensity at the half filling. It's different from these 2/3 or -1. So it means the state itself from both transporter from optics means it's compressible. So if I compare the data with the results from 2D electron gas, and they share similarities, right? So let's look at these 2D electron gas systems. You see there's signals at the 2/3 fillings, and there's signals at right. There's a plateau at 2/3. There's another plateau at the the 3/5. Then when you keep tuning the magnetic field, right, you had these -1 half filling with a suppressed RxX, and with this RxY cross two edge of these squares. So this is very similar to what we have here. When we tune the filling factor, we see the first state, which is 2/3 filling. The second is 3/5. Then we have these RxY cross two edge of these squares. Yes.
Question. So in these like 2-DEG systems, the mobility is often like a figure of merit for how.
Yeah. So the initial one, I think it's tens of thousands,
Yeah.
and even better, hundreds of thousands. But now the stability is 5 million, 6 million.
For these.
Yeah. For these, our good crystals at 5,000.
Okay.
No
So
comparison.
no comparison.
So yeah, not the same quality. Yeah. But that's also amazing, right? Even without these, millions of mobility, we already see. I will highlight these things, right? We already see pretty nice states, yeah. So shows that the gap is really large. Yeah.
Okay.
So in the 2DAC system, where there's a lot of work being devoted into the field, and the current understanding is that this state, the 1/2 filling, is a composite from a liquid state. So this shows that the state we see at 1/2, at least share some similarities of these 2DAC system. There's also theory work from the group Liang Fu and also from the group Ashwin and Daniel Parker, right? They independently show that in twisted MOT2 bilayers at the 1/2 filling, the ground state is a composite from a liquid. So at least from a theoretical point of view, the state actually exists. But I'm not claiming that our data demonstrate these. All I'm saying is there's a possible ground state. It's at least a composite from a liquid state. So what I'm going to show you today is extra evidence to sort of support this interpretation. At the 1/2 filling, the possible candidate is a composite from a liquid state. So what I'm going to show you is these optical measurements. And the paper is going to come out soon. You will see, if you don't understand what I'm saying today, hopefully you will take a look of details there. So let me just first bring you back to the basics. We know that for the TMD systems, as I mentioned to you, they have these valley-dependent optical slash rules. And for the plus K valley, coupled to sigma plus peroxide, and minus valley coupled to sigma minus. So for a TMD, if there's no spontaneous time reversal symmetry breaking, then both plus K and the minus K valley, they are energy degenerate. If I dope the system, with whole doping, as I show here, and then I shine linearly peroxide to the system, I will create the two copious triangles. One is a minus K valley triangle, the other is plus K valley triangle. They are equally populated, because I shine linearly peroxide and doesn't break time reversal symmetry of the system. Then we look at the light emission of the system. Both valley will emit an equal amount of sigma minus and the sigma plus. Then we'll see on circularly peroxide. However, in a system, if we break the valley degeneracy, for example, we have these ferromagnetism has a spontaneous spin valley polarizations. Then we have these firm level will cross one valleys. In this case, if I shine linearly polarized light again, then actually we only create one copy of a triangles, as I show here. Then we look at the light emissions. Then now the light emission should be spontaneously circularly polarized, okay? Because the system has a spontaneous time reversal symmetry breakings. So we basically measure these helical circular polarization resolved luminescence from the system. Now I first set my experimental condition at these ferromagnetic metal phase, and on the right-hand side, I shine linearly polarized light. Then I probe the system with sigma plus and sigma minus resolved measurements. And the data is taken at the zero magnetic field. Okay? So you can see that the signal is dominated by sigma minus polarized light. Okay? Sigma plus is quenched. So as I show you, basically the system has a spontaneous ferromagnetism, with a spontaneous circular polarization of the light emissions. We can also prepare the magnetization pointing down. Now you can see the helicity of the light actually switched. Now it's dominated by sigma plus and sigma minus quenched. And all the data taken here is at the zero magnetic field. So we can plot the degree of polarization. Here, degree of polarization is determined by the luminescence intensity difference between sigma minus and the sigma plus and normalized by the sum. Then we plot this degree of polarization as function of magnetic field. You will see the signal, shows nice hysteresis, That just tells you this spontaneous circular polarization is coming from the ferromagnetism, in the systems. Now, I'm going to show you, what I'm going to show you next is the degree of polarization as function of a filling factor and also function of electric field, Before I show you, I want to just highlight that you can think of these circular polarization result measurements. It's also like a dichroism measurements, but just for light emissions, in contrast to the light absorption I just told you. So there's something actually remarkable. If I look at the degree of polarizations as function of a filling factor, and the dope, as function of filling factor horizontal and the electric field in the vertical axis, they show some dramatic difference compared to these circular dichroism measurements in the absorptions. In absorption, we know that the whole phase space is ferromagnetic. But in the degree of polarization of these Tron emissions, you see that the degree of polarization is strongly suppressed at the filling factor -1, and suggests that these fractional chains are -2/3, and the phase space near 1/2. You look at the degree of polarization, right? They also show these hump feature 2/3 filling very much similar to the circular diaprism. But the only difference is either this changeless state and this half filling state. So I can just take line cuts to show you the degree of polarization as function of filling factor. These clearly show you the degree of polarization is suppressed, right, at the filling factor 1, at the -2/3, at the -1/2, and there's another feature, the -4/9 fillings, okay? But other than that, the degree of polarization close to 1. And they eventually just, vanish because the ferromagnetism vanishes, right? So how do we understand these features? Okay. So first, we can go look at the filling factor -1, right? This is simple to understand. So as I talked to you at the beginning, right, at the filling factor -1, we have this quantum anomalous state, means the bulk is an insular state, right? There's a gap opens. So when the gap opens, means the Fermi surface got gapped out. Then for the triangle formation, as I told you at the beginning, right, you need extra carriers. Now all these spin valley polarized carriers actually got gapped out because these incompressible states. The other way to think about it is the number of free spin valley polarized carriers is reduced because of the formation of these incompressible states. Therefore, right, the triangle, the valley polarized triangle is also suppressed because of the suppression of these spin valley polarized carriers. So these just leads to this suppression of luminescent intensity at the same time, and also suppression of the degree of polarizations. So similar idea can be used to the FCI state. Now, the interpretation I use here is right, the gapped states, right, suppress these free spin valley polarized carriers. Now you would imagine that if we reduce this gap, then the number of free carriers should increase, right? Therefore, the degree of polarization actually should increase if I can reduce this gap. So that's what I want to show you here is we measure the degree of polarization as function of temperature. Okay, from the bottom to the top, actually we increase the temperature. So you can already just focus on this feature at the -2/3 filling. You can see that we see a suppression of degree of polarization at the 1.6 Kelvin. But I start to increase the temperature. Actually, the degree of polarization come back, reaches the 1 at the 2.5 Kelvin. Then eventually got suppressed when the ferromagnetism vanishes. So if I plot the degree of polarization as function of temperature, as I show you here, right? Initially it was suppressed, then eventually revived to 1, right? At the high temperature means when the gap closed, and then drop again when the ferromagnetic order vanishes. So I can compare this data with my transport measurements of RXY. Right? In the transport measurements, RXY start to deviate from condensation between 2 to 3 Kelvins. That's exactly where we see these polarization revive to maximum, around between 2 to 3 Kelvins. So that's when the gaps start to close. Then we can go back to look at the degree of polarization also at the -1/2 fillings, right? And I highlight here in these orange dots. You can also see that the degree of polarization is suppressed at the low temperature, then eventually approach 1 and drops again when the ferromagnetism vanishes at the high temperature. So we can also compare these measurements to RXY as function of temperature. You can see these RXY actually start to deviate from these 2 H square around 2 Kelvins. That's exactly where we see when the charm polarization actually becomes normal. Okay, so when the gap is closed. Then we can also look at the electric field dependence. So first, I highlight these electric field dependence of degree of polarization at the ferromagnetic metal phase. So you can see that the degree of polarization basically remains maximum across a large electric field range, and eventually vanishes when these ferromagnetic states disappeared. Right? There's electric field induced phase transitions from these ferromagnetic states to non-ferromagnetic state. On the right-hand side, I plot the measurement of this MCV. in the presence of these pump laser for obtaining these luminescence, because we are worried about whether these pump laser actually can create this spin depolarization, like a photo-induced depolarization. But you can see that there's looks like quite smooth, right? There's no photo-induced effect. Then we can look at the degree of polarization as function electric field for the 2/3 state and also for the -1 state at the bottom. You will see the degree of polarization is suppressed at the small electric field and it become right close to 1 near the phase transitions, meaning the gap is small or closed, then eventually vanishes because ferromagnetic states vanishes. Then we look at right-hand side is, again, right, these MCD measurements in the presence of these pump laser. You can see there's no such of, suppressed. There's no dip features for these MCD measurements. So it means that this photo excitation actually doesn't give you this effect in my optical luminescence measurement. So lastly, I'm going to show you this feature from these -1/2 fittings. Again, right, you will see that there's a dip feature, suppressed luminescence polarizations at the small electric field, then revive, and eventually suppress again. So, but for the MCD, there's no such features. So it means the magnetization basically doesn't change during this process. So clearly, right, these -1/2 fitting, the behavior is also, if I don't tell you it's -1/2 fitting, it will look like very much like these -2/3 fitting states, right? So this suggests that these -1/2 fitting share similarities of these -2/3 fittings. So sort of maybe there's a gap in the system. But from the transport measurements and from my polarization insensitive optical measurements, we know that this half filling the state is compressible. There's no gap. So what's going on? So we look into the literature, and it turns out that this CFL state actually has a local exciting, has a charge gap, or you can think of it as a pseudo gap. So here I highlight the work from Eisenstein, right, back to 1992. So you look at the tunneling of a double layer to the electron gas. So at the zero magnetic field, you will see the tunneling is as strong as the zero bias, when the two firm level is aligned with each other, so the density of states is aligned. And the high magnetic field, the 13 Tesla, so both double layers, right, in the half fillings. Then they found out the tunneling actually, the maximum tunneling is a shift away from zero bias to 5 millielectron volt. Okay? So this basically shows you that there's actually a charge excitation gap for these CFO states. And when they raise the temperature, these features actually start to vanish. Okay? So, and I follow these experiments. There's a theory from Bert Hoblings and later on also from Reid. They explain basically in the system, you can think of these composite fermion as a dipole pictures. Right? You have a charge, you have a vortex, and they form a dipole. When you break up these dipoles, like local charge excitations, then you need to inject energies, right? So there's a pseudo gap of these composite fermions. So we can use these to explain our data, right? Basically, when exciton come in, it's neutral, and they need to steal a charge from this composite fermion liquid. But because this local excitation gap, the pseudo gap, right? Then this trion formation need to overcome this gap. Okay, so that's why, right, the behavior of these the feature near 1/2 states is very much look like this fractional chain-size state. So the other way to think about it is we can use trion as a local charge excitation probe. So that's the take-home message. Okay, so that's the end, right? I just want to highlight, as Alan talked about yesterday, I think a fractional quantum anomalous Hall is a new addition to the quantum Hall families, right? And, at the early 1980s, right, we have this remarkable discovery of these quantum Hall effects, and in 2013, right, there's discovery of this quantum anomalous Hall effect, and last year we showed that there's a fractional version of this effect in twisted MOT2. So I will conclude my talk with this phase diagram. I think there's a lot of exciting things we can do with these systems. And this is just what we can understand right now. I think there's a lot more, proposed by theories, and a lot more we haven't even thought about, right? So the axis here, vertical, is the twist angle, horizontal is the filling factors. Everything I talked to today is in the first 10 band, and the twist angle around like 3.7 to 4 degrees. But there's a lot of work, already, humidity at the high twist angles, and you heard it from phi-ESD, from small twist angle, and even from filling factor, right? Beyond the first chain band, you can go second chain band, third chain band. There's a lot of interesting physics. So I'm pretty excited about these systems. With that, and I would like to thank all my collaborators who made the contributions to this project, and also thank to all these 3 students who made a major contribution to the talk I give to you today, and all the students who work on this project. And thank you for your attention. Yeah.
Is this on? Yes. Questions?
So what is special about molybdenum ditelluride, maybe both on the theoretical side and experimental side, that led to all of this? Is there something chemically special about the material?
I can tell you what I learned, right, from theorists, is the bandwidth of twist MOT2 is very narrow. It's about 1 to 2 millielectron volt, depends on twist angle, right? Yeah. And if you look at the twist WSC2, is only out of 10 millielectron volt and larger. So even though these TMDs, they're all similar, and they make you, if you twist them, right, it's flat. And you heard yesterday, you can see superconductivities, etc. But for fractional chain state, I think the end is you want to have a chain band look like lambda levels. So it means you want it as flat as possible, I think. Correct me if I'm wrong, Alan. Yeah. So I think MOT2 is, in that sense, it has a really flat band. Yeah.
Yeah. So what sets up the high temperature scale of the fractional quantum Hall here? Is it related to the
it's an
dielectric
interaction,
constant?
basically.
Hmm?
It's an interaction. It's an electron.
So dielectric
interaction.
constant.
Dielectric constant, it's one thing. Is how strong is carrier interaction in the 2D limit, right? Because this reduces the screening effect. Electron interaction is very strong. That's give rise to all phenomena as you heard right during this conference. These superconductivities, weak crystals, all the other fantastic things. Because
Why a similar argument doesn't apply to the 2D electron gas based?
Yeah, in the gallium arsenide, right? It's still in the bulk. Even though it's a 2D system, but it's a bulk. It's a quantum well. The dielectric constant is much larger. Yeah.
So you talked about the various trends in the polarization of the luminescence.
Yeah.
What about the overall strength of the illumination of the luminescence?
Intensity, you mean?
Yeah.
Yeah. So intensity-wise, we haven't looked into details of temperature, but what we look in detail is 2 things. One is the doping dependence. The other is magnetic field dependence. Yeah. So doping dependence, right? As I talked today, that you will see the suppression when there's a thermodynamic gap, right? And then you can do a Venn diagram to look at this strata formula of these changeless state.
Yeah, I was thinking about the fractional filling trends in particular.
Yeah, exactly. Yeah, so we'll see the suppression of luminescence, and we'll see the shift of the peak.
Okay.
That's what we see when there's incompressible state. Yeah.
Other questions? We've let this table dominate. No? Okay.
Maybe related to this previous question. So these are topological effects, and disorder is not supposed to kill them, as you showed in your first slide, with a very old device. The fractional quantum Hall effect states are topologically protected, so they're not supposed to be so sort of disorder dependent. Is it possible that the new samples you made with smaller level of disorder have actually different doping, and that's what gives us the appearance of the new 2/3 state, and it's not
No, the
disorder?
initial doping is not a really matter here because we have to dope it to 10 to the 12th, right? Much larger than whatever defect give to you. Yeah, yeah. Yeah, yeah.
Still have a few minutes for discussion.
So the analogy between the composite Fermi, anomalous composite Fermi liquid
Yeah.
state and that of what's found in 2 DAGs, right, is
Yeah.
is very compelling. But what else do we kind of know about it? Maybe this, as I understood, I was interested in this some years ago. Things like cyclotron mass, temperature dependence of the resistivity. What do we know about it in this
Yeah,
regard?
so
It's really
so
quite a
temperature.
remarkable thing.
Yeah, exactly. So we don't have the cyclotron mass here because we cannot measure on the quantum oscillations here. Okay, so we don't have that. And in terms of temperature dependence, right, as I show you, we have these RxY, right, increase and eventually saturates at the 2h square as we reduce temperature. And correspondingly, Rxx will start with a value and then drops and also saturates to a value of a few kiloohms. Depends on samples from few kilohm to 10 kilohm-ish. So it means it's a metallic state. Yeah. So that's all we know. Yeah.
So quantum oscillations, there's no prospects for doing those kinds of experiments because too much field just kind of kills it.
So we can do quantum oscillations, but they need to go very high field. Yeah. We haven't been able to get it basically for this particular 1/2 state. Yeah. So we don't know anything about sectional mass.
Some of these
yeah.
other kind of canonical experiments that are for Fermi liquids like Karinga law and NMR, maybe these kinds of things.
Yeah, yeah. So I think in the 2 DAG system, right, what's really did is they do these, surface occluded wave, or these self-focusings, all these arrays of dots, etc. measurements to probe these Fermi surface, right? Show there's Fermi wave vectors, etc. So that's one possibility, but we haven't got it yet. So what I show you today is I feel like there's an other opportunity to probe these states unique to these twist MOD2, really unique to these spin valley physics. Yeah.
So, Xiaodong, yeah. Have you compared the transport gaps of the gene sequence states? How does they vary from filling factor 2/3 to 3/5 and 4/7?
We haven't done that for this new sample, but for the older sample, we compare it with 3/5 and 2/3, just 2 data points. Actually, they follow the fraction quantum Hall, the trend. Yeah.
Thank you.
Yeah. But 2 data points doesn't mean much. Yeah.
All right. Let's move on to our next talk. And thanks, Xiaodong,
thank you.
again.